All right, guys, so today we will discuss section 2.5 of our textbook, which is titled The Fundamental Theorem of Algebra, okay? It has the word fundamental, so it kind of seems like it's a big deal. So let's go ahead and make sure that we talk about that. All right, first of all, let's go ahead and start out with the definition. So here's what the Fundamental Theorem of Algebra says. If you have a function, and that function is a polynomial of degree n, where that degree is bigger than 0, then that function has at least, so I'm going to go ahead and highlight that word, has to have at least 1 0 in the complex number system. Okay, so real quick, let's make sure you remember that a complex number has the form of a plus or minus bi. Okay, remember a and I are real, a and b are real numbers. Okay. First thing I need to clarify about this. Most students believe that what this is saying is that every polynomial has an imaginary 0. That's not what it's saying. It's saying that every function has at least 1 0 in the complex number system. So, for example, if you find that x equals to 2 is a 0, that is part of the complex numbers. Think about it. It's like saying plus 0i. So it makes, like, you can get it to look like that form. You don't have to have an imaginary part in order to be considered part of the complex number system, or vice versa. You don't have to have a real number in order to be considered part of the real number system. Okay, so let's go ahead and start out with an example to show you that this is true. So let's say that you are given x cubed plus 4x and you're asked to find the zeros. Well, the power of 3 here dictates that you should be expecting to have at most 3 zeros, and based on the fundamental theorem of algebra, you should at least have 1. So let's go ahead and find out how many we have. We could have maybe 1, we could have maybe 2, we could have maybe 3. Okay, so we're going to have x to the third power plus 4x. We're going to set that equal to 0. We're going to be able to pull out an x, which will leave us with an x squared plus 4 equaling to 0. And we're going to set each one of these equal to 0. So x equals to 0 and x squared plus 4 equals to 0. So for this one, we're done. So there you go. I've at least shown that we have at least 1 0 in the complex number system. This number 0 can be written as 0 plus 0i. Now this one, I can subtract the 4, which should give me that. And then I can take the square root of both sides, which would, the fact that I have a negative means this is going to be imaginary. The square root of 4 will be plus or minus 2i. So that tells me that I have 2 more zeros, and then this one would be 3. So this one happens to have exactly 3 zeros. One of them happens to be completely real. The other one happens to be completely in the imaginary. But they are part of the complex number system. And that's really all that the fundamental theorem of algebra says, that every polynomial has to have at least 1 0, and it has to be in the complex number system. Okay? All right. So the fundamental theorem of algebra leads us to our next theorem, okay, which is very similar to the fundamental theorem of algebra. So let's go ahead and read this one. So this one's called the linear factorization theorem. So what it says is that if you have a function that is a polynomial of degree n, where n is greater than 0, so very similar to the fundamental theorem of algebra, then f has to have precisely n linear factors. N. So what that means is that if the degree was 3, you're going to have 3 linear factors. If the degree was 4, you're going to have 4 linear factors. So what does that mean? Is that if you were to actually factor out an expression, so which we have been doing in class, and then I'll show you how to put it back together here in just in a second. We're going to do an example. You're going to be able to write all of those factors multiply next to each other, right? So this is just a mathematical way of showing how it would look, right? So you have one factor times the other until you get to your last factor, depending on to what degree this is, right? So we're just giving a general example, which is the nth power. So I don't really know where to end here, so we're going to end at n, right? Because we don't know how many. N could be 10, n could be 20. So that's why I have this dot, 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 which means that if the power is 20, I'm going to have 20 of these factors, right? What this is representing, C1, C2, C3, Cn, those are representing the complex numbers or your zeros, right? Remember, to find your zeros, your first factor, you set that equal to 0, right? So this is going to represent your roots. And then a sub the n is going to be a constant, right? So you could have a constant all the way in front of this, okay? So let's do an example of what I mean by that. So let's say that you are told to find a third degree polynomial with the given zeros. So let's say you are told that x is equal to 3, x is equal to -5, and x is equal to 0. Okay, so the first thing is, and let's go ahead and say that we're going to leave your answer in, sorry, as a product of linear factors. So what that means, guys, is that we're going to leave our answer as just a bunch of factors that are multiplied. We're not going to actually multiply them out together. Okay, so first of all, right now what I have is my zeros. So what I need to do is I need to turn those zeros into factors. So this would be like saying x minus 3. This one would be like saying x plus 5. And that is like saying x plus 0, x minus 0, which is just x. So literally, what I'm going to be able to do is I'm going to be able to say that f of x is equal to x times x minus 3 times x plus 5. Notice how this has 3 zeros, which means it has 3 linear factors, and this would be an acceptable answer. I could have other answers. For example, look at this. It says that you could have a constant. So since I didn't give you any other restrictions, somebody could say, well, let's throw a 5 in there. Why not? 5x, that would still give me a 0, that would still give me a 3, and that would still give me a negative 5. So it still have the same zeros. It still meet all the requirements. It's just you change this, which is going to have a little bit of a change there on the graph. However, it still have the same roots. Okay, so which will lead me to basically another example I want to do very similar to that. But before we get to that, we need to talk about something along the words of imaginary zeros. Okay, so here's what happens. If you are given a 0, so let's say that one of your zeros is a plus bi. So you're being told one of those zeros is a plus bi, which means it's going to have some imaginary part to it. Then automatically a minus bi will also be a 0 of the polynomial. Okay, this is called conjugate pairs. Okay, in other words, imaginary zeros come in conjugate pairs. Okay. Now, why is it that they come in conjugate pairs? So that would need to be that we need to refresh a little bit about complex numbers. So let's do an example, and I'll tie it back. So let's say that you are given the following complex number. So let's say that you have 2 minus I. Okay. Its complex conjugate would be 2 plus I. Now, why do they come in pairs? So let's just talk this through. Let's just say we're going to multiply these two numbers together. So 2 minus I times 2 plus I. Okay, if we multiply that together, that gives me a 4 plus 2I minus 2I minus I squared. Okay, notice how the 4 stays, the 2I and the negative 2I are gone, and negative I squared is the same thing as negative of negative 1, which then gives you a positive 5. Notice that by me multiplying these two complex numbers that have an imaginary component to it, the result yields out a real number with no imaginary, right? So it's like saying 0i. Think this through. When you start any polynomial, you never see an I in the middle of it. However, you're going to find out very soon that when you're solving polynomials, you could have zeros that are imaginary. So how is it possible to have an imaginary 0 if we didn't have any imaginary at the beginning, right? So think that through, right? If it's possible that you can find an imaginary number, 0, from an expression that everything looked like it was real numbers, then it should make sense that if we're going to go backwards, so for example, if we were to use this idea of the linear factorization theorem, so in other words, if one of my zeros was imaginary and then I turned it into a factor and then I was to actually multiply all this out, there shouldn't be any i's left on that. Okay, so let's do an example of that to show you what I mean. Okay, so let's pretend that you are given the following information. Okay, let's say that you are given let's see. Find a third degree polynomial such that it contains the following x-intercepts. So that would be x equals, let's see, what do I have here in my example? I have x equals 2 and x equals 1 minus I. Okay, but it's going to have another requirement, and that polynomial has to have the point 1, 3. Okay, so let's see what this means. Okay, first of all, I was given two zeros. So I have this 0 right here, and then I have that 0. I notice that one of my zeros is a complex imaginary. So by default, I need to know that if x minus I is a 0, I'm sorry, x equals 1 minus I is a 0, then x is equal to 1 plus I is also a 0. Because imaginary zeros come in conjugate pairs. So that was something that I needed to realize. And now at that moment, then I realized that I have 3 zeros, which is going to help me find a third degree polynomial. So that's going to help me with that part, and then we'll talk about what this means here in just a second. So let's go ahead and tackle this down. So x equals 2 is the same thing as saying x minus 2. Now this part right here, it's like saying x minus 1 plus I, and this one would be like saying x minus 1 minus I. So that would give me this polynomial. I would have those as a product of linear factors. So notice how it says power of 1, power of 1, power of 1. So these are linear, and it's a product. Okay, so my linear factorization theorem there is working, but I could also have a number in the front, right? So I kind of forgot to put that, a sub n. Cool? Now, I'm going to go ahead and multiply this out to kind of clean this up. So let's say that we have f of x is equal to a sub n. Okay, I'm going to leave this x minus 2 by itself. Now, anytime you're going to multiply things out, I recommend that you actually multiply the conjugate pairs together to make this a little easier. And I'm actually going to go to the side and show you a little trick. You know, for example, that you can write these two together as x equals 1 plus or minus I. Right? So instead of writing them separately, I could write them as 1. So what I'm going to do is I'm going to show you a little trick so that I don't have to do all of this multiplication here and maybe get lost. If I subtract the 1, that leaves me with the I on that side. Right? So what I'm going to do is I'm going to square both sides at this point. So x minus 1 squared is going to give you an x squared minus a 2x plus a 1. And then whether it's positive or negative, if you square I, you're going to get an I squared. Okay, remember I squared is equal to negative 1. So that gives you x squared minus 2x plus 1 is equal to negative 1. If I add it to this side, then that gives me x squared minus 2x plus 2 is equal to 0. Well, guess what? If you multiply that times that, you're going to get x squared minus 2x plus 2. Okay, so hopefully that tip helps you out. Now I'm going to continue my multiplication. I'm going to leave that a sub n in the front. So then I'm going to have x times x squared gives me an x cubed. X times negative 2x gives me a negative 2x squared plus a 2x minus 2x squared plus 4x minus 4. And I'm just going to leave that in there. I'm not going to actually multiply that here yet, but I am going to combine like terms on the inside of the parentheses. So I have x to the third. Let's see, I have minus 4x squared. I have a plus 6x and a minus 4. So far I have achieved the fact that I have a third degree polynomial that has the following zeros. So now I just need to match this last behavior. Well, think about it. If I wanted to have the point 1, 3, that means that f of x, it's f of 1 equals to 3. I don't know why I put a comma in there. Where f of 1 is equal to 3. Then I know that the y value, that's 3, and that's my x value. So what I'm going to do is I'm going to plug in this into y. So that's 3 is equal to a sub n. And I'm going to plug that in for x. So that gives me a 1 to the third power minus 4 times 1 squared plus 6 times 1 minus 4. Okay, so that's going to give me a 3. That a sub n still in the front. 1 to the third is 1. 1 squared is 1 times negative 4 is negative 4. 6 times 1 is 6. So that gives me minus a 4 there. So 3 is equal to a sub n. All right, so we have 1 minus 4. It's going to give me a negative 3. Plus 6, that's going to give me a positive 3. Minus 4 is going to give me a negative 1. Which then means that a sub n is going to equal to negative 3. So now I can go back and write it. F of x is equal to negative 3, and then you have x to the third minus 4x squared plus 6x minus 4. That's from this statement right here. And then I can distribute the negative 3, so that's going to give me f of x equals to negative 3x cubed plus 12x squared minus 18x plus 12. And that would be a polynomial of degree 3 that has the given zeros and passes through the point 1, 3. Okay? So I know that was kind of a lot that happened there, but I don't think it was terrible. So let's go ahead and make sure we recap on this. Number one thing is if you are given a imaginary zero, its complex conjugate will also be there. So if you have 1 minus I, 1 plus I would be there. Okay? You can turn all of this into factors. Remember, a trick for when you have something like this to just multiply it all out, or you could just multiply that by that. You can multiply everything out. Remember that you can have a constant in front, and we're going to need to figure out that constant by using this point. After you do all your multiplication, you can plug in for x and for y. So that's where my y is. There's my x. Clean that up. Once you figure out what that constant can be, you can go back and replace it and multiply everything in. Which that leads us to our very last problem that we're going to do for this part of the chapter. And this is what I'm going to close out this video with. Okay? It should make sense that we've been studying all of this, how to find zeros, how to find end behavior, what complex numbers are, how do they work, this idea of the fundamental theorem of algebra, so that we can do one thing. Remember, our main goal for this chapter was, can you sketch the graph of the polynomial? Okay? So now, with this problem, we should be able to attack with all of our knowledge now that we have. There's nothing that we don't know that's going to stop us then from solving this problem. Okay, so let's go ahead and get started. In order for me to sketch this, I'm going to need to figure out my end behavior first, and that is going to be determined by the leading coefficient and the power. The power is 4, which is even, and the leading coefficient is positive 1. So a positive leading coefficient with an even power will give you end behavior such that it is going to be rising, left, and right. So I'll come back to this. Okay, so in order to sketch, we need our end behavior. We also need our zeros. So I'm going to set this equal to 0. And in order for me to solve this, I look at this, I'm like, this is very intimidating to try to factor, right? So in order for me to factor this, I'm going to use the rational zero test, or the rational zero theorem. So I'm going to first find my possibilities. So my possible rational zeros. If you're watching this video and you don't know what this is, then I suggest that you go back and watch the video over the rational zero theorem. Okay, so remember, to find the possible rational zeros, we're going to take the factors of your constant, which in this case is 22. So that's going to be plus or minus 1, plus or minus 2, plus or minus 11, plus or minus 22, and divided by the factors of your leading coefficient, which in this case is technically a 1. So that's a plus or minus 1. We're going to divide all of these numbers by 1, so that gives you plus or minus 1, plus or minus 2, plus or minus 11, and plus or minus 22. So remember, this right here are just possibilities. So now we're going to use synthetic division to help us figure out which ones are actually zeros. Remember, we can use the idea of the remainder theorem to help us out. Remember, the remainder theorem tells you that if the remainder, whatever the remainder is, that's what the evaluation would be at that point. So in other words, if we want to figure out whether or not this is a 0, the remainder should be 0. Okay, so let's go ahead and set this up. We're going to put a 1 here for the coefficient of x to the 4th, a 3 for the coefficient of x to the 3rd, a negative 5 for x squared, a negative 21 for x to the 1st, and then a 22 for x to the 0. Okay. Now, which one of these you try, it really doesn't matter. It's up to you. So you can either follow your intuition, you can do a little bit of mental math, but really you just got to try. Okay. So I'm going to go ahead and start off with 1. Okay. See what happens. So I'm going to do 1. 1 times 1 is 1. 3 plus 1 is 4. 4 times 1 is 4. Negative 5 plus 4 gives you a negative 1. Negative 1 times 1 gives you a negative 1. Negative 21 minus 1 gives you a negative 22. And negative 22 times 1 gives you a negative 22, which then automatically gives you 0. Therefore, we know that x is equal to 1 is a 0. Okay. Now, remember, once you finish the division, if you were originally on the fourth power, then that means that you are down to a third power. Okay, so you have a decision to make. You can try to see if you can factor out this third power polynomial, or you can continue to use these possibilities to see what happens. What I typically do is I continue exactly from where I left off, and I always try this number again. Why? Because if it is a zero that repeats itself, then not only am I going to find out the multiplicity of this, but it's going to help me continue to bring down the power. So I'm going to try it. It doesn't mean that it's going to work, but let's see what happens. So I'm going to bring down the 1. 1 times 1 is 1. That gives me a 5. 5 times 1 is 5. 5 minus 1 is 4. 4 times 1 is 4. And I can automatically then tell the fact that I got a negative 18, that means that this is not a 0, so it doesn't repeat itself. Okay? So I know I just kind of wasted some time there, or maybe not wasted time. I wanted to try to make sure to see if it could save me time. Fortunately, it did not. So I'm going to go back and use these numbers and try another one of my possibilities from here. So I've got this 1, the 4, the negative 1, and the negative 22. So now I'm going to try the 2, see what happens. So 1 times 2 is 2. 4 plus 2 is 6. 6 times 2 is 12. 12 minus 1 is 11. 11 times 2 is 22, which gives me a remainder of 0. So therefore, x equals to 2 is also going to be. So now, really what that means is, okay, if this was to the fourth power and I've done 2 divisions, what it means is I can start writing this as the product of linear factors. Okay, technically I have x minus 1 from this one, right? So this gives me x minus 1. This one gives me x minus 2. And from this one I can get x squared plus 6x plus 11. Okay, so now I have this 2 as linear. I still need to continue to factor, or try to factor this out to get my zeros if I want to continue and graph. So I'm going to go ahead and continue, but this is a quadratic, so I'm noticing, first of all, that there is nothing that I can multiply to be 11 that would add up to be 6. So I'm going to use the quadratic formula for this, or you can use completing the square, whichever technique you feel more comfortable with. So I'm going to go ahead and share both. Okay, so let's say you want to do quadratic formula. So x is equal to negative b plus or minus b squared minus 4ac all over 2a. So in this case, b is going to be 6, so that's going to be negative 6 plus or minus the square root of 6 squared minus 4 times a, which is 1, times c, which is 11, all over 2 times a, which in this case is a 1. So I'm going to go ahead and continue. So that gives me a negative 6 plus or minus the square root of 36 minus 44 all over 2. So that means x is equal to, I'm going to go ahead and separate this 2 out, negative 6 over 2 plus or minus the square root of, so 36 minus 44. 36 minus 44 is going to get us a negative number. Okay, so that is going to get us a negative 12. No, what am I doing? I'm sorry. Negative 8. My apologies. Brain fart. Sorry. Negative 8 over 2. Okay, now I can further continue, and negative 6 divided by 2 is going to give you negative 3 plus or minus. The square root of 8 is the same thing as 2 root 2, but because it was negative, I'm going to have an I in there. I still have this 2. The 2 is going to cancel out, which gives you negative 3 plus or minus root 2i. So let's go ahead and recap what happened here real quick before I show you the other technique. So far we found that x is equal to 1 is a 0, x is equal to 2 is a 0, x is equal to negative 3 plus the square root of 2i is a 0, and x is equal to negative 3 minus the square root of 2i is a 0. That's 4 zeros. The beginning statement or polynomial was to the 4th degree, so I have successfully found all of them. I could rewrite this as factors, and this would be x minus 1, this would be x minus 2, this would be x plus 3 minus root 2i, this one would be x plus 3 plus root 2i, and if I put them together and I multiply them out, this would be products of linear factors, and if I multiply all that out, I should be able to obtain this. Okay, but that's not what we're doing. I just kind of wanted to recap that. Okay, now let's go ahead and show you the other technique of finding these 2 zeros out, which is completing the square. So if I go back, this quadratic that I was dealing with was this. Okay, So if you want to use completing of the square, first of all, ensure that the leading coefficient is 1, which in this case it is. Okay? Number 2, we're going to take the constant, move the constant to opposite side of your equal sign. So in this case, I'm going to take the 11 by subtraction. So that's going to be x squared plus 6x. And I'm going to subtract the 11 and take it to the other side. Now notice how I'm leaving in space. That's because we're going to be looking for a number. We're going to complete the square. If you want a further explanation of what this works, I would suggest that you look up the proof of why completing the square works. It's not what this video is about, so I don't want to take so much time explaining why it is that this works. I just want to kind of show you how it works. Okay? Now, this number right here, remember, is considered b. Okay? So what you're going to do is you're going to take b, you're going to divide it by 2, and you're going to square it. Okay? And that's the number that you will put into this space. So if you take 6, you divide it by 2, that gives you 3, and you square, you put a 9. Well, think about it. If you're going to add a 9 to this side of the equation, you have to add a 9 to the other side of the equation to balance it out. Okay? So what that does is then you should then be able to factor this into x plus 3 times x plus 3. And on the right-hand side, you're going to have a negative 2. Okay? So why is this called completing the square? Notice that the two factors that you found are exactly the same, so you can rewrite it as a product of, instead of a product of two linears, you can just write it as a square, hence completing the square. And then we're going to take the square root of both sides, so that gives you x plus 3 is equal to plus or minus root 2i. We're going to subtract the 3, so that gives you negative 3 plus or minus root 2i, which then notice that gives us the exact same solution that we had found with the quadratic formula. Okay? If you have any more questions about how to find zeros by completing the square, I would suggest you look up another video regarding that specific skill. Okay? But let's go back to the original problem, which was like, can you grab this? Okay, so let's go back. So we had x equals 1, x equals 2, x equals negative 3 plus root 2i, and x equals negative 3 minus root 2i. Now, these are my zeros. How many times does this one show up? Well, this has a multiplicity of 1. It showed up once. This one will have a multiplicity of 1. Now, this one's, because they are imaginary, and for the purposes of this course, we are not going to be concerned of what this does to the graph. So, these zeros, they are zeros. I need you to know that they are zeros. But as far as the graph goes, I do not actually need you to know what it does to it. So the multiplicity of them does not matter for this. So really, now we just have to go back and use our information from the beginning, which is what was the end behavior, which you guys said that it was rising left and right. So I'm going to go ahead and plot this information. So let's say that that's 1, and let's say that that's 2. I know I have a 0 there. I know I have a 0 there. Because the multiplicity here is odd, I am going to cross. And I am going to cross this one as well because the multiplicity is odd. So what I know is my end behavior is I'm supposed to be rising on the left hand side. Because this function is a polynomial, I know that it's continuous, so I have to approach this value. Now, according to this information, because the multiplicity is odd, I'm going to cross at that place. Now, for the purposes of this course, once again, we're not going to discuss of how low this needs to go, so we will talk about extrema in calculus. Okay, what I do know is all I have to do is turn around very smoothly, and in this case go towards 2. When I get to this root, I need to cross, and then this matches my original statement, which is this thing should be rising to the left and to the right. Now, is this exactly what this polynomial looks like? Not necessarily, but it does give you a general idea of what it kind of looks like. Okay, remember, for this chapter, I'm not looking for exactness. I'm looking to make sure that you can at least connect this idea of, hey, the end behavior needs to match the roots, and you should have a relatively close sketch of what it looks like. Okay, to get a better sketch, you will need to learn some calculus in order for you to find out maximum, minimums, points of inflection, etc., etc. But at this point in your math career, this is the best that you can do. Okay, all right. So I don't want to make this video any longer. I want to make sure that you actually get some practice. So with this examples, I think is good enough for you to get started and try your homework. So that's all I got for you today, and I will see you guys next time.